Atomic structure, looking at the pieces of the atom and how we put it together. Looking at the evolution of the atom and where we got our ideas from, the atom begins its identity or its concept with the Greek philosophers Leucippus and Democritus back in the 5th century. They came up with the idea that matter was not completely 100% infinitely divisible. There was a limit to its divisibility, and they called this limit atomos, which was a Greek word, or is a Greek word, for indivisible, which they theorized or hypothesized was the smallest composition of matter that you could get. Now, this idea became lost for a long time in the dark ages of medieval Europe, but was eventually resurfaced a little bit more down the road as we began to explore science more after the Renaissance. Robert Boyle was the first one to really make advances after this in the idea of the modern element, what we understand as things like oxygen and gold and salt, or sodium and chlorine, and these different elements. Until then, we had the classical notion of elements, the fire, earth, wind, water, that you may be familiar with. But Boyle advanced this notion of elements as we understand them in modern terms. In the 18th and 19th century, John Dalton came up with what we call atomic theory. This is the idea, a 6-point idea or 6-tenet idea, that all matter consists of tiny particles called atoms. And these atoms cannot be created, divided, destroyed, or converted into other types of atoms. Atoms of a particular element have the same properties. They are completely identical. Atoms of different elements are different in their properties. Atoms of different elements will combine in simple whole number ratios to produce compounds. And chemical changes involve joining, separating, or rearranging atoms. Now, of these 6 points, 2 of them are not always true, as we now know. An atom can be created, divided, or destroyed, or converted, and we do this through nuclear chemistry. And we know by the discovery of what we call isotopes, or different types of atoms of a particular element, that we can have different properties within the same element. For example, the isotope carbon-12, the isotope carbon-14 have different properties. Carbon-14 is what we call radioactive, and carbon-12 is not. The rest of this theory holds true, and most of the theory works well in particular chemical situations that we're going to look at. Now, when we look at the evolution of the atom, through Dalton, we had this understanding that the atom was a single component, kind of like a marble. But we now know that it is comprised of several components, and these components were discerned by different experiments by different physicists and chemists throughout the years. The composition of an atom is now known at its subatomic level to be 3 particles. The proton, which was discovered by Eugene Goldstein, and is a positive particle with a mass of 1.0073 atomic mass units. The neutron, discovered by James Chadwick, which is a neutral particle with an atomic mass of 1.0087. And the electron, discovered by J.J. Thomson, which is a negative particle with a mass of 5.489 times 10 to the negative 4 atomic mass units. So you see the combination of the proton and the neutron makes up the vast majority of the mass of an atom, while the electron contributes only a small amount. Usually, particles or atoms will be neutral. They can build up charge or static electricity, but they will always try to equalize that. That's why you have static discharge. That's why you have combinations. If you do have charged atoms, like ions, why the negative and the positive atoms will move towards each other in order to neutralize or equalize charge. Now, the ratio of these 3 particles in an atom give the atom its particular properties. We can identify an atom as a particular element by its proton, because that is the only one of the 3 which will not change within an element. The numbers of neutrons will change depending on the isotope, and the number of electrons can change depending on whether the atom is an ion or not. Looking at our further understanding, what was originally theorized was, once we began to look at the atom as not a uniform thing, there was originally what we call a plum pudding model that was advanced by Thomson. This is the idea that the atom consists of a large amount of positive matter in which negative electrons are just kind of studded. If you think of something, if you're not familiar with the plum pudding, which is an English thing, think of like a blueberry muffin. A blueberry muffin has the muffin with a lot of little blueberries stuck in it. That was kind of the idea of how an atom was put together. eventually, Ernest Rutherford began running experiments with gold foil where he bombarded the foil with what we call alpha particles. And he found that these particles were not just bouncing off the way he expected. Some of them were being sent in strange directions. Some of them were even being sent backwards at the original source, so kind of deflected off, like it reflected right back at him. And he was astounded by this, and he came to come up with what we call a nuclear theory. The nuclear theory theorizes that matter is not uniform. It's another example of this, or another advancement in this idea that matter isn't uniform, and it consists of 3 points. The first is that most of the mass and all of the positive charge in an atom is contained in a central nucleus. The second is that the atom is mostly empty space, that you have a central nucleus and a lot of empty space around that nucleus. This empty space contains negative electrons that are dispersed through it. Now, nuclear theory does not tell us how those electrons are arranged, but it does say that they are outside the nucleus. And we know that the number of negative electrons equals the number of positive protons when we're looking at a neutral atom. Now, when we look at a nucleus is 99.9% of the atom's mass. It's kind of like the idea of a water droplet that is dispersed in a cloud. If we're looking at clouds, these are these individual little water droplets. That is how the atoms are arranged. The nucleus, if you think of its just relative the size of a nucleus, if you put a small dot on a piece of paper with a pencil, the electrons would be up to 10 meters away from that dot. So it's a very large empty space. The size of a grain of sand comprised only of nuclei would weigh 5 million kilograms. So the nucleus is very small but very dense. The nucleus is anywhere from 10 to the negative 14 to 10 to the negative 15 meters in diameter. Now, compared to the size of the atom is usually 2 times 10 to the negative 10 meters, or what we would say 200 picometers, or 2 angstroms in diameter. So the nucleus is considerably smaller than the atom as a whole. The density of the nucleus is very high, 2.4 times 10 to the 14 grams per cubic centimeter.